In the last video, I've explained how the movements of the electrons and holes can change the resistance around the junction of this setup, this P and N connected together setup, so that current cannot flow when the battery is connected one way, and current can flow when the battery is connected in the opposite way. So this actually is the action of a diode, right? It is the function which we call a diode. So let me draw a picture. That's the symbol for a diode. Okay, a diode. Now, let's see. This is the direction in which current cannot flow. This is the direction in which current can flow. So a diode symbol is represented by a triangle pointing in the direction of that the current can flow in, a line here, and the wires joining to it. So that is the symbol for a diode. Okay, so this triangle, which looks like say an arrow in this direction, the direction of this arrow tells us the direction that the current can flow in. So in this case, current can flow this way, but current cannot flow this way. So this is a diode. Okay. Okay. Now the other thing, before I finish off with this topic, the other thing I would like to describe is how the potential changes across this as we go through this PN junction. Let me start from there. Okay, I need to clear off some space. Okay. Oops. Right, I would like to describe how the voltage changes across here. Perhaps starting with this unconnected PN junction. So in this PN junction, this is not connected to any battery yet. Okay. So let's say I want to try and draw a graph. A graph of potential against X. Let's say X is this direction here. Okay, so now see, there are these negative charges here and there are these positive charges here. So in order to understand how the voltage would look like, let's remind ourselves of a similar situation which we have seen in the earlier videos under electricity and magnetism, where I talked about the parallel plate capacitor, or just parallel plates. Remember that in the examples there, I had I've talked quite a bit about parallel plates in which are connected to positive and negative poles of battery, and the result was that there were these positive charges on one plate and negative charges on the other plate, and then we have electric field, right, going from positive to negative plates. Okay, so in that example, might be easier if I change this to positive. Okay, let's say positive charges are here, negative charges are here. So there are these electric field in this direction. Okay, and I've already sketched in one of those videos a graph of potential against X, and you might remember that let's see, if you are talking about, right, if you are talking about, say, positive charges, the potential for a positive charge, then the potential will be higher here and lower there. Okay, because remember that the force is always directed towards lower potential. So that's one way to look at it. The other way to look at it is that if I start from here and I want to bring a positive charge over to the other side, I have to do work. So as I move a positive charge from here to here, the potential energy increases. Just like if I lift up a stone. If I lift up a piece of stone against the force of gravity, the potential of the stone increases. The potential energy of the stone increases. So if I bring a positive charge, what I'm trying to do is to understand which way around the potential will increase. So if I have a positive charge, which I bring from left to right, I would be going against the repulsion from the positive charges here. If I bring the positive charge from left to right, its potential would increase. Right? Its potential would increase. So if I have a graph, want to plot a graph of the potential for when I move from left to right, move a positive charge from left to right, the graph would go up. Right? The graph would go up, and it would go up in a straight line, because if you remember, force is equal to work done is equal to force times distance. Okay, and the potential is basically work done per unit charge, right? So, and distance here is just the distance along here, which is the x. So it's actually F times x. Okay, so that's directly related to the potential, to charge times potential, in fact. So that means that if I want to plot a graph of V against X, it would be a straight line. Right? It would be a straight line. It would be a straight line in this case, which looks like this. Okay. And that's in between the plates. But what happens when the positive charge moves beyond the plate? Alright, I can either make a small hole and bring it through, or I can just quickly bring it around and carry on. So anyway, when the positive charge is moved over to the other side, what's the potential then? Well, if it's on the other side, then it will experience no force. Alright, assuming that these two plates are quite wide compared to the movement here, because when the positive charge is here, the force it would experience from the negative and the positive charges in the two plates would cancel. Okay, so if there are no more forces when the positive charge is here, when you move it, you don't have to do any more work. So there will be no more change in the potential. So as far as the graph is concerned, there's no more change in the potential, so it would just stay horizontal. And likewise, if this is on the other side, there's no change in the potential. So that's what a graph of the potential would look like for the parallel plates, for this parallel plate setup. Now, if you compare this with this, the two are not so different. We have a layer of positive charges here, just like positive charges on this plate. Layer of negative charges here, just like the negative charges on this plate. Okay, so the understanding from the parallel plates can be transferred directly to the PN junction. We can apply it directly to the PN junction, and the graph would look just the same. The width of the plate, the distance between the two plates will correspond to the width of the depletion region. Let me just write this part out. So this width D would correspond to the width of this depletion region, called D. Okay, and that corresponds to the region between this point and this point. Okay. Right. So now let's go over to this setup where I've just connected the battery in this way, in such a way that the current cannot flow. Oh, by the way, let me just mention, I should just mention something, which is that if the battery is connected in this direction so that the current cannot flow, this direction, this direction of connection has a name. Actually, it's called a reverse. Spelling this very well. It's called a reverse bias. Whereas in this connection, in which the battery is connected in a direction that allows the current to flow, this way of connection is called a forward bias. A forward bias. Okay. So I want to take a look at how this graph, this potential graph, would change when in the reverse bias. Okay, so let me try and copy. Let me just try and copy this graph over. Let's now consider how this voltage graph would change when we have the reverse bias. If you look at, if you compare the depletion region here with here, the obvious difference is that the width of the depletion region has increased. so it is now wider. It is now wider. So this means that the V, this region, this lobe here, this slanted line, which was from here to here at first, would now become wider. Right? It should now become wider. Okay, so the new graph would therefore look something like this. Okay, so that would be the difference in this case. And in this case, we can imagine that it would just be the opposite. Okay, since the depletion region has shrunk, right, it has become smaller, we would expect a graph where this slanted region spreads over a much smaller region. Okay, let me try and draw that quickly. So what we have here is just a depletion region. Maybe that would be a tiny bit, or maybe hardly any. In any case, we just extend over a very small region. So that's how it would look like. It's a very short depletion region at most, or hardly any. That's X, and that's the V. So I think this completes the videos on PN junction.